Hey, physics students, I wanted to show you a really interesting demonstration that I was finagling with that I think will help explain this relationship between frictional force and normal force. So let me show you what I'm doing with that. Before I get started, I'm going to go ahead and show you what I want to show you just a couple basic things with the free body diagram and try to talk a little bit more about what mu, the coefficient of friction, actually means. So first of all, the equations that we're dealing with, we've got the equation for kinetic friction. The force of kinetic friction is equal to normal force times mu k representing the coefficient of kinetic friction. And then the force of static friction for when things are stationary is less than or equal to normal force times mu s, so the coefficient of static friction. First of all, what mu, or the coefficient of friction, actually means, it's a ratio between the frictional force and the normal force. Yes, there we go. So frictional force divided by normal force tells us this coefficient of friction. So basically what the coefficient of friction is, it's a value, just a number that we multiply times normal force to figure out how much frictional force would be required to move something. And that mu changes depending on the surfaces that are acting on each other, rubbing together, or in static friction case, trying to rub together, trying to slide past but not quite succeeding. Now, before I do my demonstration, I want to talk to you guys about my free body diagram here, the forces that are acting on this object. Let me draw it a little bit bigger so that you guys can really see it. It doesn't look quite big enough on the screen. So if I've got an object, we know if it's on Earth, what's always acting on it? The force due to gravity. Now that's better, I can see it from here. And we know if, like, say, I have my flask, that this object is going to have the force due to gravity acting on it. It's in equilibrium because it's not accelerating up or down. It's at rest, actually. So not only is it not accelerating, it's also not moving. And so that tells me that the normal force acting on it is going to be equal in size or magnitude to the force due to gravity and opposite in direction. So I'm going to put that negative there. Remember, Fn is equal to negative Fg because it's in the opposite direction. Okay, so those are the forces acting on it in the vertical direction, and right now there's no other force acting on it. Let's say that I go ahead and apply a force to my flask to have it moving with a nice constant velocity. If I do that, then we've got a label here, Fa, for F applied, so the force that I'm applying. And then we also know if this is moving with a constant velocity, then there has to be some force acting against it, which is my force of friction, trying to slow it down. And so that force of friction, if this is moving with a constant velocity, has to be equal in size and opposite in direction to my force applied. Not every single one of our friction problems will have that be the case. It will not always be moving at a constant velocity. Sometimes it will be accelerating, speeding up, meaning the applied force would be greater, or slowing down, meaning the frictional force would be greater. So those are other options, but right now we're just going to focus on the constant velocity part. Okay, so that's what's happening free body diagram style. Now let me go ahead and get to the demonstration, and for that, we're going to be using our Pasco data, and I'm gonna make this frame. Oh, sorry. Where am I? Ah, there I am. I want to make this just a little bit. Oh, come on! Sorry, guys. I am not going to re-record this because I have been trying to do this too long. Okay. Forget it. maybe if I make this thing smaller, move that over here, move this over here. Yay, that'll do. Now let me tilt this down so that you can see the table better where I'm doing my demonstration. There we go. Okay. So what we're going to be looking at is not only the force required to slide one of these objects along, but we're also going to look at the normal force that would be needed to support them, so that we can look at this ratio. This mu is my force of friction divided by my normal force. All right. So I got 3 objects. 2 of them are made out of the same material, so they would have the same types of surfaces rubbing together. And then I've also got this very tough surface. It's rubbered bottom, so it's very difficult to slide. So we're going to try that out. Let me go ahead and hit record. And so what this graph is recording, this is showing me, I'm going to try to spread the time out a little bit so we can see it better. What this graph is showing me is the force that the force sensor is having to apply. And remember, these are the same force sensors that we used in the elevator. If we pull outward on here, that is a negative force. Pushing in would be a positive force. So that's what we're looking at here. Okay. To try to keep this nice and balanced, let me hit the tare button, make that 0. And now I'm going to go ahead and try to see how much force would it take just to support this flask. How much force would be required just to support it? So, i.e., what I'm trying to figure out here is the normal force. Okay. Okay. So what that's showing me, the drop in force there is showing me how much force is required, or how much force is actually pulling down on the sensor. So I can see how much force would actually be required to support this object. So this is telling me my normal force. Now let's see how that compares to the frictional force that it would take to get it to slide. So here we go. Hooked on. And now I'm sliding the object along. Now do you see that there is still a drop to show us that this object is applying a force? And so there is a force of friction acting on the object, but it's very, very, very small, especially compared to its weight or its normal force. So what that tells me, if we know that the coefficient of friction is, no, you probably can't read that at all. If the coefficient of friction is my frictional force divided by my normal force, this is telling me my normal force is going to be much bigger, so my coefficient of kinetic friction here would be a very, very small number. Now let's try another example. Let's do this, this flask that's the same material, but it's just larger. So if it's larger, we know it's probably going to have a bigger weight and require a bigger normal force to support it. And, in fact, it does. So you can see how much farther that force is, how much farther the force sensor is being pulled down, the greater amount of force that's being applied to the force sensor right now. So the normal force that the force sensor has to apply is much bigger. Okay, now let's compare that to the frictional force. Do you guys think there's going to be more or less frictional force here than there was with the smaller flask? How come? I wish I was there to hear. Okay, you ready? Give it a little bit more space. Tare, I think we're good. All right, now I'm going to start applying this force. Is it a bigger force? Looks to me like it is. But it's still relatively very small compared to the weight of the flask. Now, since these objects are the same substance, I would assume that them rubbing on this table would have the same coefficient of friction. because it's the same types of surfaces rubbing together. So that ratio of frictional force to normal force should be the same for both of them, and we're not going to calculate it. But if you look at the graphs, it looks pretty much like that's the case. All right, the last one I'm going to do is this object, and for this object, I want to remind you about, can we see this equation here? Maybe just a little bit. Okay. Remember that static friction, the force of static friction, is less than or equal to normal force times mu s. So when I get ready to start pulling on this object, what you'll see is that at first, if I'm not applying any force, you don't see any change, and then I start pulling a little bit, and you guys can see that the force is dropping down, right? And I'm pulling harder and harder, and this tape dispenser is not moving yet. Well, you can't see it because I need to tilt the thing back down. Okay. Force is increasing. Tape dispenser is still not moving. Still not moving. Still not moving. But the force is increasing. And now finally it's starting to move. Look how big that force is that it takes to get this thing to slide with a relatively constant velocity. Yikes. It's a big force. Okay. Some pretty good data there. So this time I've done the frictional force first. Last time I was doing normal force first. So let's compare the frictional force to the actual force required just to support this thing to its weight, or its normal force. Look at that. What's very interesting about this is look at the difference here. To support this, to support the tape dispenser, it's not even having to pull as much as it did to get this object to slide. Do you guys see that? Do you guys see how right here, this is not as big a force as this. It actually takes more force for the object to be slid along the table than it does for the object to be just supported in air. So what that tells me is if we think about this relationship here, the frictional force in the numerator is bigger than the normal force in the denominator. We're actually going to get a mu, a coefficient of friction, that is greater than 1. Most of our coefficients of friction will probably be less than 1, because it makes sense that normal force is probably, to actually support the weight of something, is going to be more than it takes to slide it along, so the frictional force. But that's not always the case. And with this rubberized bottom here, that is exactly what's happening. Okay, as you can see, I'm running out of battery, and I don't want to bore you any longer, so I think we're going to call that a day. I hope that that was useful, and we'll see if we can do it again sometime. All right.